Hi there, everybody. Today we will be going through quantitative changes in equilibrium. So how this differs from what you've done before is, with Le Chatelier's principle, you examined qualitative changes, how concentrations will increase or decrease, and we didn't go through quantifying them. So it's a qualitative property. Through this lesson, we're going to review how to calculate the changes and evaluate where an equilibrium is in its progress. So our goal is to use the reaction quotient Q to determine the state of a reaction, if it's at equilibrium, before equilibrium, or if it went past equilibrium somehow. We'll describe which way a reaction will proceed to reach it, how it will adjust itself, and then we'll do a couple of calculations, a few different ways with different tricks to simplify the concentrations that we set up in the nice table. So we'll do a quick recall screen here, and the idea is that we have a balanced reaction where A and B react to C and D, and we had our equilibrium law expression, which was the products over the reactants. So this is specific to equilibrium, which is why the EQ is there. At any other point than equilibrium, so if we have a graph here, right, we just see products and reactants. Got our reactants there and our products there. Where the reactants are changing, that will be the ratio at equilibrium. That's what KEQ is describing, products divided by reactants. But at any other point, right, let's assume this point here, we can't call that K because K represents the equilibrium scenario. But there still exists a ratio of products to reactants. It's just not the proper ratio where the change stops. So the ratio at any point other than equilibrium is called the reaction quotient, and its term is Q, and it's still the same formula, products divided by reactants raised to their exponents. So again, what we're interested in and what we've learned is that equilibrium reactions reach a certain ratio, and when they reach that ratio, the concentration stops changing. But before that point, there exists ratios as well, and the reaction quotient analyzes those. Okay, so we'll notice that it's the same formula. We'll jot that down, but instead of K, it's Q, and this is when we don't know if a system is at equilibrium or not. So if we compare that here, Q, which is called the reaction quotient, is the current ratio of products to reactants. What we'll do is compare it to the value of K, which is known for the reaction, and it'll help us identify what's going to happen with that reaction. So if Q and K equal each other, that means the system's at equilibrium because everything's in the proper ratio. And you can see the double-headed arrow is the same, which means the reactions are happening in equal rates. If Q is ever greater than K, remember that it's a ratio of products over reactants. So if Q is too large, that means the numerator is too large. We have too many products formed for what equilibrium should have. So the system will turn some of those products back into reactants and shifts towards the reactant side. Right, so depending on what the system is, that scenario looks different for every reaction. And then if Q is less than K, right, we have that ratio of products to reactants here, that means the denominator is too large relative to the numerator. So we have to turn more reactants into products, so the system will shift towards the right side. Okay, so the calculations are the same. It's how we interpret what the value is. So we use Q to determine if a system is at equilibrium or not. Okay, we'll just is it at equilibrium? Okay, and the scenarios below, by comparing it to K, allow us to do that. So we need the value of K for it. So if we look at this, this is just a visual of what we just said, right? If Q is less than K, Q needs to increase to be equal because Q represents the ratio. So the ratio has to go up. So it shifts towards the right. If Q is greater than K, there's too much product. It has to lower the ratio by turning some into reactants. So it shifts towards the left. And don't forget, shift left and shift right just tell us which side of the reaction gets produced. Because they're reversible, we can make and consume either or. So let's look at an example here. We'll go to a Word document for a little bit more room. Examining this and the fact that K is given to us in the question as 0.020, right? We're asked very simply, is the system at equilibrium? Right? So what that means in this case to determine that is compare the value of Q to K. So we're given the following concentrations. They're not equilibrium concentrations. Okay, they can be, but they're not necessarily. So we're going to determine if they are. If Q is equal to 0.02, which is the K value, then those are equilibrium concentrations. If not, then the reaction's not finished. So we'll say this. There's our reaction at the top, right? If we look at it, we should balance it, right? So we'll have a 2 in front of that. And now we've got a balanced reaction. So we'll say Q is equal to the products over the reactants. We've got H2 over I2 times HI, and because it has a coefficient, it's squared. So we have our numbers here, 0.04, 0.01. And again, I'm just leaving out units for simplicity here, but they're all moles per liter. Okay, and when we evaluate that value, punch it in, okay, go through it slowly, we'll find that Q is equal to 0.02. So what does that mean? Well, if we compare Q to K, they are equal. So we can say this system has the correct ratio and is at equilibrium. We'll just write that there. All right, and proper ratio means that we won't see any more changes. So let's do the exact same thing for different concentrations now. So a different point in the reaction, these just represent different times. So we have the same formula as above. I'll rewrite it. Okay, products over reactants. Okay, so in this case, let's just punch our numbers in, 0.15 times 0.09, 0.20 times 2. Okay, and when we calculate that, we'll find that Q, 0.3375. So what this means, if we compare Q to K, right, Q is larger than K, because K was 0.020. That means I'm just going to simplify this, there's too much product, because the ratio is too high. So the reaction will produce more reactant in this case. And to do that, it will shift, so you can guess if you haven't yet, left. It'll shift towards the reactant side. And that means we'll lose concentration of the products and gain it of the reactants. So that's how we calculate the value of Q itself. Right? And that's what this represented. Calculate Q. And that'll determine if a system's at equilibrium or not. Now, we'll use these concepts to do a little bit more of a complex equilibrium calculation. So we're going to step away from Q for a second, and we're going to go to the ice tables in K. All right, we'll apply everything that we've learned so far, right, using K and the ice table to determine concentrations. And remember that an ice table helps us to determine what the equilibrium concentrations are. So we could pause there at this example, and that's just what the reaction quotient actually is. All right, and that's kind of like the first half of this here. So I'll stop at this point, and we'll come back and we'll do some more complex calculations.